Now, another simple method for ascending an alcohol means increasing the carbon number by 1. Introduction of ACS2 group. Now for that, the alcohol is first converted to the alkyl halide by reaction with PCl5. RCl is obtained. Then with magnesium in ether, we get RMgCl, that is Grignard reagent. Then that is reacted with the formaldehyde. The R part, which is negative, goes to CS2, and MgCl part goes to oxygen. You get RCS2 MgCl, which on hydrolysis catalyzed by acid, we get RCS2OH. Now how will you convert benzene to benzyl alcohol? Now for that, benzene is first of all chlorinated using chlorine and ferrichloride as the catalyst. We get chlorobenzene. Then with magnesium in ether, we get phenyl magnesium chloride. It's a Grignard reagent. Then further reaction with the formaldehyde, this splits like this. The phenyl part goes to CS2 and MgCl part goes to oxygen. Then we get phenyl CS2 or MgCl, which on hydrolysis we get C6H5 CS2OH, phenyl CS2OH. So that is benzyl alcohol. So benzene to benzyl alcohol via Grignard reagent. Now chlorobenzene we know is a resonance hybrid, and we have seen that carbon to chlorine bond is having double bond character. And how this chlorine breaks away from the benzene ring to incorporate a magnesium atom directly bonded to the ring. Now, magnesium is a divalent metal, in the sense it has 2 valence electrons. Now, it is a reactive metal. After the alkali metals, which are more reactive, then comes alkaline earth metals, that is magnesium, beryllium, magnesium, calcium, etc., which are slightly less reactive. And magnesium donates 1 electron to the benzene ring, that is this carbon here, and this chlorine is removed as Cl negative. And chlorine is removed as Cl negative, this carbon should get a positive charge, and that positive charge is neutralized by donating 1 electron from magnesium. Then magnesium gains a positive charge, and the charge over this carbon is neutralized because it is getting 1 electron. Now then chloride ion establishes a bond with Mg positive, so that both these charges are getting neutralized, and this unpaired electron combines with this unpaired electron to get a bond between magnesium and benzene ring. Now it is a free radical type reaction. There, this reactive metal donates electron to the benzene ring system, so that the electron density from chlorine is blocked. So plasma effect is blocked by donation of electron by magnesium to this carbon. So this bond no more becomes a double bond character a bond having double bond character, so that a free radical mechanism favors the formation of phenyl magnesium bromide. So that is formation of benzyl alcohol from benzene. Then how will you convert ethine to ethanol? Now ethine, that is acetylene, another name for ethine, can react with a molecule of water in presence of dilute sulfuric acid and mercuric sulfate as catalyst at 60 degrees Celsius. Now we can convert 60 degree to Kelvin temperature. 60 plus 273 gives 333. That's a fancy number. We can remember 333 Kelvin or 60 degrees Celsius. A molecule of water adds to this one, and here we can say H2O is getting added. So water splits into 2H and 1O. So the two pi bonds here break. So this carbon possesses two valencies and this carbon possesses two valencies. The two valencies over this carbon is united with the two valencies over oxygen to get C double bond O. Now the two valencies over this carbon obtained by breakage of two pi bonds will combine each with a hydrogen atom, so that the two valencies combine with the two hydrogen and we get CH3 and CHO. Now if water splits into H and OH, then H connects to this carbon and OH connects to this carbon. We get aniene, then ol, aninol. Now enol can undergo a type of rearrangement called tautomerism. So that this bond, OH bond, will be shifting in this direction. The valency of this carbon will rise to 5. To make the valency 4, this bond will be shifting over this carbon. In the sense, this carbon takes up the pair of electrons in this bond and gets a negative charge. Now during this shift, the hydrogen atom is left with a positive charge. So this negative carbon combines with the positive hydrogen, forming a CH bond, and this group becomes CH3 and CHO, and this aldehyde called acetaldehyde can be reduced using lithium aluminum hydride to ethanol. So that is some simple conversion reactions. Now coming to the chapter on aldehydes and ketones. Now the speciality of aldehydes and ketones is that both contain a C double bond O group, which is called a carbonyl group. And so the reactions of aldehydes and ketones are similar. Similar reactions are given by aldehydes and ketones because they both contain a C double bond O group. We call it a carbonyl group. Now here in the case of aldehydes, the aldehyde group is C double bond OH. C double bond OH. It is monovalent. Whereas ketonic group is C double bond O with divalency. So C double bond O divalency. So we cannot connect the ketonic group at the end of a carbon chain, but we can connect it in between two carbons, whereas the aldehyde group can be connected at the end of a carbon chain. Now coming to the IUPAC naming of some compounds. When such a compound is given, the preference is given to aldehyde carbon. See, the order of preference of various groups is COOH, and then comes CHO. There are in between these two there are some other groups, but the common groups which we are familiar with, the acid group is given preference over aldehyde group. So here the aldehyde group is given preference number 1, and then you number the carbon chain such that this branch and this branch are included. So this is 1, 2, 3, 4, a butane derivative, parent hydrocarbon is butane. Now you add the suffix al, al, to the parent's name, omitting the last letter E. So if it is butane, you omit E, the last letter, so butan, and then add the suffix al, butanal. Suffix means something added at the end of a name, and prefix means something added before a name. So here al is the suffix of aldehydes, and the suffix of ketone is on, so we can say butanone. And here an example for a ketone, and the parent here is chosen as 1, 2, 3, that is propane. You omit the last letter E and indicate the number of carbon on which the double bonded O starts, that is the ketone group. And here carbon number 1 is on, so propan 1 on, and on carbon 1 there is phenyl group, so 1 phenyl propan 1 on. Now if both aldehydic and ketonic groups are present, then preference goes to CHO group. CO group comes next, so that then the ketonic group is not considered as on, but the prefix oxo is added before the name. Prefix means something added before, so that when you number the carbon atoms, giving number 1 to the CHO carbon, 2, 3, 4, there is 3 oxo. 3 oxo. Oxo means O double bonded structure is called oxo. So oxo means O double bond. So on carbon 3 there is oxo group. 3 oxo, butan, 1 al or butanal. That is, if the locating number is 1, then we want to specify the number if it is a functional group. If CHO group is considered as a substituent, the suffix carbaldehyde is used. So we can consider CHO as a substituent, then we add the suffix carbaldehyde. Now an example given here, that is 3 aldehyde groups connected to a propane parent, 1, 2, 3. On 1 there is CHO, 2 there is CHO, 3 there is CHO. So the parent is propane, 1, 2, 3 tricarbaldehyde. So we are not numbering the CHO groups. Similarly, in the case of this compound, there is benzene ring, and on carbon 1 and 2 there are 2 CHO groups. So this is called benzene 1,2 dicarbaldehyde. Similarly, this compound, which is a cyclohexane derivative, you start numbering from the carbon to which CHO group is connected. So 1, 2, 3. So this 3-methyl cyclohexane 1-carbaldehyde, or simply carbaldehyde. If it is number 1, we won't specify that number. Now the carbonyl group in aldehydes and ketones is a resonance hybrid of 2 canonical structures, so that the resonance hybrid possesses partial positive charge over carbon and partial negative charge over oxygen, so that the carbon atom of a carbonyl group shows nucleo-loving character. It is not nucleus loving character. No, it is not nucleus loving character, but electron loving character. So it is electrophilic in nature. So carbonyl carbon is electrophilic in nature and oxygen is nucleophilic in nature. Now coming to the preparation, oxidation of primary alcohol gives aldehydes and oxidation of secondary alcohol gives ketones. Now here one difficulty is that when we try an oxidizing agent, a strong oxidizing agent like acidified potassium permanganate or acidified potassium dichromate, then the aldehyde formed will be more easily oxidized. So we have to prevent the oxidation at the stage of formation of the aldehyde. So we cannot use strong oxidizing agents. We have seen this in the case of the reactions of alcohols. And we can use chromium trioxide in anhydrous medium. Usually chromium trioxide is soluble in alcohol and ether. So this may be preferred as the anhydrous medium, alcohol and ether. And then another reagent used is pyridinium chlorochromate. You have seen this compound in the case of alcohols. In dichloromethane, that is a solvent used, and we can write an equation RCH2OH giving RCHO. So that is oxidation plus these two hydrogens are converted to H2O water, complete equation. Then dehydrogenation reaction, we have also seen this in the case of the reactions of alcohols. When we pass vapors of alcohols over heated copper, or again we can use the metal silver, metallic silver, copper at 300 degrees Celsius. If a primary alcohol is passed over copper heated to 300 degrees Celsius, we get an aldehyde. If a secondary alcohol is passed over copper heated to 300 degrees Celsius, we get a ketone. Then it is dehydrogenation reaction, so that two H atoms are removed as H2, this H and this H is removed as H2, so RCH2OH gives RCHO plus H2, CH3CHOH CH3 gives CH3CO CH3 plus H2. It is dehydrogenation reaction. All these reactions are the reactions of alcohols. And again we can prepare either aldehydes alone or aldehydes and ketones or ketones alone by choosing appropriate alkenes and subjecting the alkene to ozonolysis, that is addition of ozone followed by hydrolysis. And for hydrolysis we use zinc and water, and zinc is used because hydrogen peroxide may be formed as a byproduct. And zinc dust destroys hydrogen peroxide because hydrogen peroxide is an oxidizing agent which can easily oxidize the aldehyde formed. Now the net reaction is breakage of the double bond and addition of two oxygen atoms. So the position of the double bond is getting broken, and then two oxygen atoms are added to the carbon atoms possessing this double bond. So this example CH3C double bond CH3, we get oxygen here and oxygen here, CH3CO CH3, CH3CO CH3 and CH3CHO, C acetone and acetaldehyde are formed. So all these reactions were studied earlier. Now an important reaction, that is Rosenmund reduction, it is called. And here an acid chloride means it's a derivative of acid. You treat an acid with BCl5, the OH group in COOH will be replaced by a chlorine and we get acid chloride, CH3COCl. It is called acetyl chloride, is an example for acid chloride. It is reduced using hydrogen and palladium supported on barium sulfate. Now here barium sulfate is acting as a poison to the catalyst palladium. Now because the CH3CHO formed may be easily reduced by hydrogen and palladium to the corresponding CH3CH2OH, that is primary alcohol. To prevent this, we are using palladium on barium sulfate. In barium sulfate, it is said that it has a low surface area, and the catalytic activity of a catalyst is directly proportional to the surface area of the catalyst. And here palladium supported on barium sulfate is prepared by reacting palladium chloride PdCl2 with formaldehyde in aqueous medium to get palladium. In presence of barium sulfate, this reaction is conducted so that palladium will be deposited on this barium sulfate precipitate, which has a low surface area. So palladium is formed by reduction of palladium chloride using formaldehyde. In presence of water, formaldehyde is oxidized to formic acid. PdCl2 is reduced to palladium, and this 2Cl and 2H here combined to form 2HCl. So it is a redox reaction, an oxidation reduction reaction. Now the metal catalyst with a low surface area, will have hydrogen atoms adsorbed on these metals. So adsorbed means the hydrogen atoms formed from hydrogen molecule will form loose chemical bonds with the metal surface. The metal atom provides free valencies which will combine with the valencies over hydrogen and will form loose chemical bonds, not strong chemical bonds but loose bonds. So those bonds are formed between hydrogen and the metal surface palladium, which is supported on barium sulfate. Now RCOCl will be adsorbed, means will form loose chemical bonds with the metal surface such that Cl bond is broken and C is getting bonded by loose chemical bonds and Cl is getting by loose chemical bonds, and RCO is present there. Now another H here. Now that happens is that the loose chemical bond here breaks and hydrogen, and the loose chemical bond here also breaks, and hydrogen with its valency will combine with the carbon, and the loose chemical bond here will be broken, and the loose bond will be broken here, and chlorine and H losing their valencies combined. So that is the reaction of a molecule catalyzed by a metal surface. So catalytic reaction of a metal is of this type: adsorption on the metal surface and breakage of bonds, formation of loose bonds, and then withdrawal of these loose bonds and formation of bonds between different atoms. So that is the mechanism of catalytic activity of palladium supported on barium sulfate. Now simply the reaction may be understood like this: this CCl bond breaks, one H here and one H here. So we can write plus H2, CH3COH and HCl. So that is Rosenmund reduction, and acid chloride is reduced using hydrogen and palladium supported on barium sulfate, where barium sulfate is acting as a poison to the catalyst, so that further reduction of the aldehyde is made impossible. Now if the aldehyde is very reactive, another poisoning substance that is quinoline and sulfur is added to the medium as further poisons of the catalyst if the aldehyde is highly reactive. So quinoline sulfur may be added to reduce the catalytic activity so that aldehyde is not further reduced. Now named reactions are important, so you have to study these reactions, and this reaction is very simple to understand. Only thing is that barium sulfate is acting as a poison to the catalyst palladium. From cyanides or nitriles, these cyanides or nitriles can give aldehydes or ketones by a sequence of reactions, and this method is known as Stephen's method. Now their stannous chloride is a reducing agent. It reduces the cyanide or nitrile to an imine, imine, imine. So C triple bond N is reduced to CH double bond NH, animine. Now stannous chloride is getting oxidized to stannic chloride. Here the oxidation state is +2 and here the oxidation state is +4, so that this cyanide is reduced to imine. Now there the oxidation state of tin here is +2 and the oxidation state of tin in essential for stannic chloride is +4. Now suppose we take one example of a compound, say CH3CN. It is reduced to CH3 C double bond NH N bond H, we can see. So all the hydrogen atoms should be having +1 charge because hydrogens are the least electronegative among these atoms, and nitrogen is the most electronegative. So when this bond ionizes, nitrogen gets a negative charge. When these two bonds ionizes, nitrogen gets additional 2 negative charges, so that its oxidation state is -3. Then we have +1, +2, +3, +4 and +5. So +5 plus -3, that is +5 -3. Then suppose this is X, plus X equals 0, so that this carbon is having -3, so we have to add this also. So -3 plus +5 -3 plus X equals 0, so that +5 -6 plus X equals 0, so that X equals +1, we can say. Now in cyanide, here it is +1, here it is +1, here it is +1, here it is -3 for carbon and -3 for carbon, so that the total here, if it is X here, then +1 +2 +3, then +-3, then plus X -3 equals 0, so that the net charge of X will be equal to +3. So if cyanide is reduced to an imine, the oxidation state of this carbon changes from +3 to +1. That is, a change in 2 plus 2 change, and stannous chloride Sn plus 2 is converted to Sn plus 4, while in cyanide the plus 3 state is converted to plus 1. So for this reaction 2 electrons are to be removed, and for this reaction 2 electrons are to be absorbed. So that is a redox reaction. And then the imine is hydrolyzed, addition of H2O like this, and we get RCH double bond O plus NH3 ammonia. This method is known as Stephen's method. So the reagent stannous chloride, a reducing agent, acts in presence of hydrochloric acid. Cyanide or nitrile is converted to imine. Two H atoms are connected to carbon and nitrogen, and the triple bond becomes a double bond, and the imine on hydrolysis, addition of water, we get ammonia, and a CH double bond because oxygen is divalent. Then nitriles are also reduced by diisobutyl aluminum hydride to imine, followed by hydrolysis to aldehyde. Diisobutyl aluminum hydride is abbreviated as dibal H, and this H is shown here as H. Now we are having a bulky alkyl group here and here, so two bulky alkyl groups. Then this purpose of this bulky alkyl groups is not exactly known. Maybe that this compound may be obtained in a solid form, in a crystalline form, since the molecular weight is high when such groups are connected. Anyway, this hydrogen may be used for reduction. And here aluminum, since it is a Lewis acid, it can provide a vacant orbital into which electron pair may be received, and here the pi electron pair is received by aluminum. We get Al negative, so that H as H negative is getting connected to this carbon, and we get RCH double bond N, then bonded to Al. Now then this compound undergoes hydrolysis, H2 here, so that NH2 is formed, and O here, double bond O, we get RCHO, then Al, isobutyl, bond NH2 which undergoes hydrolysis. Nitrogen is the negative part because aluminum is a metal, it will carry a positive charge, so that water when splits into H positive goes to the negative nitrogen, that is NH3 is formed, and AlOH isobutyl. So that is the mechanism of reaction, cyanide getting converted to aldehyde, or nitrile getting converted to aldehyde. But simply this reaction may be written as RC triple bond N plus 2H, and this 2H indicates these hydrogen atoms. So one molecule donating one hydrogen and another molecule donating another hydrogen, to get first the imine, which on hydrolysis we can complete this bond, H2O addition, we get RCHO plus NH3. So that is the simple equation. This mechanism need not be studied. Now esters also can be reduced using dibal H, and there again the mechanism is similar. This CO bond will be shifting into the vacant orbital of aluminum of dibal, and this carbon possesses positive charge, so that this AlH bond with the electron pair, because aluminum is electropositive and hydrogen is more electronegative than aluminum, so this bond as a pair of electron can be taken up by hydrogen and bonded to carbon, so that the positive charge developed over carbon will be neutralized, and we get CHO. And when O will be getting connected to Al, so OAl, then isobutyl, then this bond will be shifting in this direction and OR2 negatively removed. So this R1 and R2 represent different alkyl groups, they may be same or different. So OR2 minus will be removed and this will combine with aluminum, because aluminum gains a positive charge when this bond migrates in this direction. So OR negative is removed so that the valency of this carbon is maintained 4. Then OR negative combines with Al positive, producing R2O Al bond. Then this may be undergoing hydrolysis like this R2OH and ALOH, 2 isobutyl groups. So that is the reaction, but again we can write a simple equation, R1 COOR2 plus 2H, here this one 1H here and 1H here, we get R1 CHO plus R2OH. That's a simple equation. Now this dibal H will not reduce non-polar bonds like C double bond C or C triple bond C. Now they are non-polar because the bonded atoms are the same, so they have the same electronegativity. Now this quality, that is the ability not to reduce non-polar bonds, is also possessed by lithium aluminum hydride, which is a powerful reducing agent in organic chemistry. C double bond C is not reduced by lithium aluminum hydride, only polar bonds are reduced. Here also dibal H does not reduce non-polar bonds like C double bond or C triple bond. So that is enough. Thank you.